everybody. So I will reuse some of the slides from our Wednesday talk. We learned about this too late to prepare a special slide deck and go through the Merck internal authorization. We are a small and young group, so mostly young colleagues, not me. And we specialize in non-specialization. We are developing methods to compose models out of component models and to provide decision support on top of that. And we view organizations as in the company or as in healthcare as similar to organisms and what happens inside, how resources are metabolized and how regulation and control is implemented. So the approach is that all decisions are based on models of some sorts. Human or organizational decisions are often based on mental models, and that doesn't really scale up. So if you explicate, if you have models of models that you can simulate and explore and build higher level models as if from Lego blocks, then there are many advantages. And that's what we are developing, the technology stack, and using for internal projects. And we use, we have a domain-specific language called DyVE, stands for the Dynamics of Value Evolution, where value in, say, the R&D or business setting typically is speed, cost, capacity, quality, and importantly also reduction of entropy, reduction of uncertainty about key aspects, key questions. And we use principled abstractions from category theory or applied category theory. We also use data structures from algebraic, Julia, and CATLAB. And with that, we can represent network dynamics at the scale of molecules or cells, but it can also be network dynamics where what moves are projects, all the way to the dynamics of clinical trials and logistics of clinical trials or population level dynamics. And so this is where we see the biggest opportunity for adding value is to compose, say, joint distribution, probabilistic approximations of what's going on at different temporal and spatial scales of the organization and the context, and provide an agential glue, so the distributed agency would account for the local regulation or decisions, and if we have a performant implementation, we can explore the space of possibilities and optimize and do forward simulation or backward Bayesian inference in that. So I cannot go into details, but in the bottom we see 3 applications in Merck research laboratories: the systems pharmacology, optimal experimental design, and then supply chain optimization in global clinical trials. And the 4th is a mention of large process modeling, where we integrated models of discovery, development, clinical trials, manufacturing, and healthcare, and in a synthetic way, synthetic but realistic, and demonstrated that neural networks combined with equations, as in SciML, could learn to optimize the trade-off between satisfying in manufacturing and supply chains, satisfying the need of clinical trials versus satisfying the need of a broader market for the manufactured drugs. So to say a little bit about the systems pharmacology, and this is just our group, this is not the standard that would be used by Merck. We pioneered the use of Julia and this. Now there are other groups in manufacturing and the trial statisticians who are interested, but it's not used in, the main practice. So we got an ODE model of a neuroimmune pathway in the brain with hundreds of variables and parameters that was developed by a vendor, and we translated that into Julia and provided our agential glue, so to decide about which combination. So there would be a series of perturbations with dosing combination of monoclonal antibodies, and over a long horizon you would optimize for the overall effect adjusted for the total dose administered. And this went smoothly, very fast, and our explorations and heuristic optimizations led to the cancellation of the whole project because it showed that the underlying ODE model had shortcomings. But what we gained confidence, so we will be engaging with new modeling tasks. And so that's about what I can say about the biology and pharmacology. What's underneath is that we generalized chemical reaction dynamics, so as in catalyst, but our reactions, or this is a special case of Petri nets, and namely open Petri nets. We have explicit delays. We can represent capacity, so how many. The reactions are quantized, so you have discrete instances. The reaction rate is interpreted as a Poisson rate, so you create individual transition or reaction instances. Importantly, the stoichiometric coefficients may not be integers, and they may be very large. So this is what we had initially trouble with, say, catalyst that we wouldn't be able to represent, say, very large coefficients or float coefficients. Yes, but also importantly, the left-hand sides and right-hand sides and other parameters of the transitions may be stochastic. So we have generative models, and you can then and of course we have callbacks, and now we are also adding agency both to the reactions and to the tokens, the species that move. These can have their own structure and behavior. So that's coming. These are all packages in the public domain on GitHub, reactive dynamics and algebraic agents.jl, and then the merger, the agential reactive dynamics is going to be there shortly. And that gives us an opportunity to model at multiple spatial and temporal scales and to co-integrate with pre-existing models that can be in SciML, in algebraic dynamics, or agents.jl and other. So if something behaves as the defect integrator or can be wrapped in a defect integrator, then we can co-integrate with our models. So that's it. So these are the main packages, and if you have questions.
Thank you very much. So, do you have questions? Questions?
Yeah, so I've seen you're doing abstractions in algebraic Julia. Can you go a bit into detail how this works? Because I think this is a very interesting topic, but like for a beginner, I have not much experience in that.
So here you can see schemata that the, say, nodes here are concepts or objects, and the arcs are relationships. So categories are networks of relationships, and with rules so that you can compose or map between such networks, and it preserves structure or property. So this is like Lego blocks that's reliable to compose. And here you see that an output arc from a reaction or input arc has two ends, the source and the target. And in inputs, the source is a chemical species or the type that goes into it. It doesn't need to be chemical species. It can be ingredients that the network may be a recipe how to bake a pie. So you take eggs and produce the white, separate the white and the yolk. And the transitions are the reactions, and they may have attributes themselves, like capacity or the time and so on. And for this, so you can add arbitrary attributes, and what you get is a representation as a relational data set that you can join with other such data sets. And so you can compose things which would be difficult or impossible to compose at the level of differential equations.
Thank you. We have more questions? Okay. If not, then let's thank the speaker again.